My name is Matthew Jones. I'm a professor in the Quantum Light and Matter group here at Durham University, and I want to tell you about an exciting PhD project that I have to offer in the area of quantum information science. So the aim of the project is to bring together two different quantum platforms to make a hybrid system that can achieve more than each system alone. In this case, one of the two platforms is a widely used platform for quantum information based on superconductors, and this platform forms the basis of the quantum computers made by Google and Microsoft and others. And the other platform is a much newer one that we're involved in pioneering, based on using excited states in semiconductors. So in the next few slides I'll explain how this works and why it's so exciting, and what you would be working on and how it will work if you came to join my group. So quantum computing is obviously a study of intense interest both in universities and increasingly now in the private sector, with the leading role being played by corporate giants like Google and Microsoft, as I already mentioned. And the machines that they have built operate at microwave frequencies, and the logical units, known as quantum bits or qubits, are coupled together via microwave transmission lines made out of high-quality superconducting thin films. You can see these quantum wires in this picture of this chip from the Zurich quantum computing group. These are the wiggly lines here, and the qubits are these little boxes, and you can see how these microwave transmission lines wire these qubits together. On the right of this slide you can see how the quantum information is mapped onto a microwave signal. The two different states of the qubit, here labelled left and right, give rise to a phase shift on the microwave signal, which is typically at about 3.7 gigahertz here. So we can read out these superconducting qubits, but the problem is that a consequence of working at microwave frequencies is that the devices must be cooled to extremely low temperatures, so about 100 millikelvin, or 100 thousandths of a degree above absolute zero, or even colder, down sometimes as low as 2 millikelvin, using an expensive helium-based fridge that's known as a dilution refrigerator. And you have to do this because otherwise the thermal background of microwave photons that exists because the chip is at a finite temperature would completely swamp your quantum signal. And what this means is it's really hard to send microwave quantum information over long distances. The whole of the transmission line, let's suppose I had two of these computers, the whole of the transmission line connecting them together would need to be chilled to this ultra cold temperature of a few millikelvin. Otherwise the thermal noise would drown out my quantum signal. And that's obviously technologically extremely difficult and would only ever really work over short distances. So what's the alternative? Well, the alternative is to use a system where the microwave quantum information can be mapped onto light, because we know we can send optical photons over global distances using optical fiber networks. That's how our modern computer networks are working, how the internet is working. And to do this, we need to build a converter that can convert the microwave quantum information to optical quantum information. So we need a system with strong coupling to microwave radiation and strong coupling to light. And in this project we propose to do this using the other quantum system. And this other quantum system are to use a special kind of excited states in the semiconductor, and the semiconductor is called cuprous oxide. So let me try and introduce these states. So semiconductors are materials with a band gap. Okay, so the electrons are sitting in the valence band, and what we do is we shine in light and we can excite an electron to the conduction band, and we say that it leaves behind a positively charged hole. And this process is exactly the process that's used to detect light in things like the camera on your phone. Okay, we excite an electron, which then on the phone gets counted in, and that's what gives you the image. Okay, but in some materials, the electron and hole combine together to form a state that is like hydrogen atoms. So here I've drawn hydrogen. We have a positively charged proton and a negatively charged electron that are bound together. So an exciton is an analogy of hydrogen, where now this is the positively charged hole left behind in the valence band, and this is the negatively charged electron in the conduction band. And so we get this series of bound states here, so that these bound states have a lower energy than a free electron that live near the band edge and that we can excite optically. So to show you how that works, I've got these two spectra. The top image here is the spectrum of hydrogen. This is the Balmer series of hydrogen. So you see the usual series of spectral lines. So this would be the n equals 2 to n equals 3 line, to n equals 4, 5, 6, 7, 8, and so on. And this plot at the bottom here is the absorption spectrum of cuprous oxide near the band gap. And these black lines here are where the cuprous oxide is absorbing the light. And what you see is that if I've stretched these to match them up, you see that we get exactly the same pattern of lines. And that's because it's the same Schrödinger equation that describes these excitons as it is that describes hydrogen. And the key point is that for high enough principal quantum number, the separation between these high-lying states, so say between n equals 12 and n equals 13, so somewhere up here, can be in the microwave region. But as you can see from the image at the bottom, we still have a strong coupling to light. So we have what we need, which is a system that couples to both lights and microwaves. And the key thing is that these excitons like to live at low temperature, and the dilution refrigerator is actually the ideal environment for them. So my group in Durham is internationally leading. We're the first group to have observed the coupling between light and microwave radiation using these excitons in cuprous oxide. So this paper was recently published in Physical Review Research. So here's some pictures of how we do the experiment. So the cuprous oxide is this black dot here, and there's a basic microwave antenna here. We cool this whole thing down to 4 Kelvin, and so we shine light through this hole here and we send the microwave radiation through this antenna. And here's what's going on. So we use the light to create the excitons, and then they get coupled to nearby excitonic states by the microwave radiation. And what we were able to show is that this changes the properties of the optical signal. So here's an optical signal generated in the cuprous oxide. The purple trace here shows the signal, the spectrum of the light. So we're scanning the frequency here and measuring the intensity of the light. So this is the spectrum. Without the microwaves, we get a single peak, which is the same as the spectrum of the light that we put in. And when we turn the microwave field on, we get these extra components at the same frequency as the microwave. So here, plus or minus 19 gigahertz away from this central carrier. So we've modulated the frequency of the light using the microwave radiation, and we can detect this modulation and perform a microwave to optical conversion. And we could send this information down an optical fiber. So the goal of your project is to push this really further and see if we can really develop it into a true quantum interface between a quantum microwave circuit and light. Here everything was classical, the light was classical, and the microwave field was classical. So we want to push this and see how far we can take it. So how would this project work? Well, the project takes place in a successful existing collaboration between Durham and Cardiff University. So you will work in the Durham team and be based in Durham, which is where we have the 4 Kelvin refrigerator and all the instruments needed to make the measurements of the spectra and how the microwaves are interacting with the sample. But you'll also collaborate in particular with the group of Simon Doyle at Cardiff. We also have other collaborators at Cardiff. And Simon Doyle's expertise is the fabrication of these superconducting quantum microwave circuits. So this picture here shows an example of a camera they've made for detecting light, where every single pixel is a superconducting microwave circuit. Okay, and so we're aiming to bring this technology together with what we've learned about excitons in Durham over the last few years, and try and deliver this hybrid system. So a few more details about the project. So it's a fully funded 3.5-year studentship that we have available for UK students. It is possible that we may be able to support overseas students, so please contact me if you fall into that bracket. Like all of these fully paid UK government studentships, you get your fees paid and you get a stipend of just over £15,000 per year, which is tax-free. If you want to find out more details about this project, please contact me via my email address here. I'll just emphasise there's extensive opportunities for travel both to Cardiff and abroad here, and you also benefit from the strong links to other groups that we have working on Rydberg atoms and systems like that in the Durham group. Thanks for your attention.